Okay, welcome to our October Ask a Physicist. We're very happy that you all have joined us, especially on the abnormal day, since we're doing it a week early because of Halloween. But next month, we will be right back on track with our normal schedule. It will be the last Monday of the month, November 28th. And we will have guest presenter Gerard Milburn. And the title is What Time Is It and How Do We Know? So be on the lookout for registration links that will open up about 2 weeks prior. For tonight's Ask a Physicist, we will be getting to questions towards the end of the hour, but if at any time during the presentation you have a question, please submit it through the Q&A feature at the bottom of your screen. And as a reminder, we are recording this and it will be posted to YouTube later. So if you would like to rewatch it or share it with anybody, just be on the lookout for that. And that's all the announcements I have. So I will turn it over to our moderator for the evening, Maulik Parikh.
Thank you, Jessica. So welcome, everyone. And today we are very honored and happy to have Nicole Yunger Halpern as a visitor and as our main speaker. And she is a theoretical physicist at the University of Maryland, and she works in the exciting new area of quantum information and thermodynamics, and she's also the author of a book that just recently came out called Quantum Steampunk: The Physics of Yesterday's Tomorrow, which you should see on your screen right now. So welcome, Nicole, and why don't we take it from here?
Thanks for the introduction, and thanks very much to the whole group for having me over. I'm really excited to share with you some of what's been happening in this new field of quantum thermodynamics. So given the questions that have been tackled in this webinar in the past, I can tell that this group is sophisticated, so I can be a little bit technical. So I'd like to begin with the technical term. Oh, my slides actually aren't working as expected. Sorry about this. Okay, I'll have to try from my computer. Okay, I would like to begin with a technical term, if my slides will allow me now. And that technical term is steampunk. Steampunk is a genre of literature, art, and film. Steampunk stories take place during the Victorian era, when the Industrial Revolution has been humming, London is full of smog and Sherlock Holmesian mysteries, railroads are cutting across the American West for the first time, and people wear waistcoats or petticoats. Against this backdrop are futuristic technologies, such as automata, time machines, and flying ships. You might have encountered this steampunk novel, The Time Machine by H.G. Wells. It's one of the first steampunk works, as it was written during the 1800s, but steampunk is very much with us still. The invention of Hugo Cabret was a New York Times bestseller in the early 2000s. Enola Holmes was one of the first films released on Netflix due to the pandemic. It follows Sherlock Holmes's little sister, Enola. The film was a hit. I loved it. And the sequel is actually coming out a week from Friday, so you should check it out. The Nevers is a show on HBO about Victorian women who have supernatural gifts. So these works reach back to the past and ahead to the future. They create this wonderful fusion of old and new that generates a sense of nostalgia and adventure. The fans dress up in steampunk costumes with top hats and goggles and gears and gather at steampunk conventions, all for the sake of what's supposedly a fantasy. But this fantasy of steampunk has become a reality in my field of research. I'm a theoretical physicist who works at the intersection of three fields: quantum physics, information science, and energy science called thermodynamics. I'll briefly preview this intersection and then talk about the different sections in more detail. The information science is the study of how efficiently we can process information. For instance, communicate messages. Quantum physics is the study of the very small, such as single atoms or ions. And they behave in counterintuitive ways that everyday objects cannot. Scientists and engineers are now leveraging these counterintuitive behaviors to build quantum computers, which will be able to process information in ways that familiar technologies, such as my laptop, can never hope to accomplish. Thermodynamics is the study of energy. It was developed during the Victorian era to describe one of the transformative technologies of the era, the steam engine. Today's transformative technologies include quantum devices, which are very, very different. So we need to ask how quantum engines would look and what they could achieve. We need to re-envision the thermodynamics of the 1800s for the 21st century. In other words, we need to reach back to the past and ahead to the future. The resulting fusion of old and new, I call quantum steampunk. So a genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. Let's look at each of those components a little more closely. Information science is the study of how efficiently we can perform information processing tasks. These include solving computational problems, such as calculating a satellite's trajectory, communicating information, such as over the web, securing information cryptographically, and storing information in memories. We live in the information age, but what actually is information? It's basically the ability to distinguish between alternatives. Say that a friend of yours asks whether the pub down the street, in Victorian London, of course, is open or closed. You peer through the window and see either foaming mugs or cleaned mugs sitting upside down on the counter. You've gained the ability to distinguish whether the pub is open or closed. You've gained information. We measure quantities in units, such as seconds or teaspoons. What's the basic unit of information? It's called the bit. It's the amount of information you gain if you have no idea of the answer to a yes or no question, and you learn the answer. Say that the pub down the street has a probability 1/2 of being open and a probability 1/2 of being closed. When you peer through the window, you gain a bit of information. We encode a bit in a physical system that can be in one of two possible states. For instance, in a familiar computer, a bit is encoded in a transistor that can have the value 1 or the value 0. Quantum physics is the study of basically very small things, such as single electrons or atoms or particles of light, which are called photons. These systems behave in ways impossible for everyday objects, such as books and microphones and human beings. Everyday objects are large, are massive, and contain many, many particles, and they're called classical. So quantum physics is non-classical. What are these counterintuitive quantum behaviors? We can begin to understand one by imagining that some young physicist, let's call her Audrey, has an electron, and her brother Baxter has another electron. The siblings can perform some operation on their particles that creates entanglement between them. Now, entanglement is a relationship that quantum particles can share and classical particles cannot. Here's a glimpse of how it works. Suppose that Audrey measures some property of her particle, and the measurement has two possible outcomes. which I'll label as 1 and 0. For instance, Audrey can measure whether her particle has a lot of energy or a little energy. If the two particles are entangled as strongly as possible, then she'll have no idea which outcome she'll obtain. 0 and 1 have 50-50 chances. Now, suppose that Audrey measures her particle and Baxter measures his. The siblings can predict now something about the joint outcome. In one example, if Audrey obtains a 1, she'll know that Baxter will obtain a 0. And if Audrey obtains a 0, she'll know that Baxter will obtain a 1. Furthermore, there is a measurement that the siblings can perform jointly on a pair of particles together, such that the siblings can predict the outcome with certainty in advance. So there's some information that isn't in Audrey's particle, it isn't in Baxter's particle, and it isn't in the sum of the particles addressed independently. It's spread across the pair. But when it comes to entanglement, the whole really is greater than the sum of its parts. By the way, this illustration, like other black and white illustrations that we'll see, are by, this is by Todd Cahill. Todd is a steampunk artist. He illustrated my book. He had no experience with quantum physics whatsoever, so the project was very much an adventure, but I like to think that he succeeded in making very imaginative illustrations, including this one. The scientists and engineers are now leveraging entanglement in quantum information processing. Quantum information science is the study of how we can process information using quantum phenomena in ways forbidden for classical systems. Quantum information technologies includes quantum computers, networks for communication, cryptographic systems, and more. Quantum computers will be able to solve in minutes certain problems that would take even supercomputers many years. Today's quantum computers are small and limited. Many of us in the field expect that will take quite a few more years to build them up to their full potential. An important application will be research and development in material science and chemistry. For instance, we invest about 3% of the world's entire energy outputs in fertilizer production. Why do we spend so much energy? Because we produce fertilizer using an old technique from 1909. Bacteria can accomplish the same goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. The molecule, though, is quantum. So a quantum computer will naturally be better suited to unlocking the molecule's secrets. And if all goes as hoped, and that is a very big if, transforming fertilizer production and energy use. Little wonder that governments across the globe are pouring funds into quantum science and technology. In 2018, Congress passed the National Quantum Initiative Act, which provided $1.2 billion for quantum efforts. Even more astoundingly, the Senate passed the act unanimously. Everyone in the Senate actually agreed about it. Like governments, companies are investing in quantum science. Microsoft, Google, IBM, Amazon, Honeywell, and loads of quantum startups have quantum teams. This object belongs to IBM. This is not a quantum computer, even though it does look cool enough to be one. Actually, many people think it looks steampunk because of the gold and copper and wires sticking out everywhere. This object holds a quantum computer which fits on a small chip. That chip needs to be at low temperatures to support quantum behaviors such as entanglement. So this device cools the quantum computer to temperatures below that of outer space. Actually, when my husband heard that, He's a classical computer scientist. He was indignant. He said, this thing cools things down to below the temperature of outer space. And by the way, this is called a dilution refrigerator, or to those of us in the field, a fridge. He was complaining that we can't even call it a freezer. Anyway, cooling leads us to the third element in our triumvirate, thermodynamics. The thermodynamics is the study of energy, the forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in two forms, heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized energy and so isn't directly useful. Work is coordinated energy that can be directly harnessed to power a factory or charge a battery or raise an anchor. Heat engines convert random heat into coordinated work. Heat engines drove the Industrial Revolution by powering the first factories. Around that era, people started wanting to know how efficiently engines could operate. So they developed the theory of thermodynamics, giving it a practical bent. However, the practical questions led to fundamental questions, such as why does time flow in only one direction? And do materials really consist of particles too small for us to see? The theory of atomism hadn't been entirely accepted by the Victorian era. So cooling, expelling heat, is a thermodynamic process. But how do you measure the heat emitted by a quantum system that's cooling? You can measure the heat emitted by a classical system by measuring the energy, cooling the system, and measuring the energy again. The initial energy minus the final energy is the heat lost. But quantum systems are more delicate than classical systems. You might have heard of Heisenberg's uncertainty principle. Werner Heisenberg was a German physicist who helped found quantum theory during the 1920s. He intuited that if you measure a quantum system, you disturb it. So if you measure a quantum system's energy, you might change the energy. So how we can measure quantum heat, or even conceive of quantum heat, is not straightforward. Furthermore, this fridge is a large classical system. Could we build a fridge from a quantum system? How small could we make it? More broadly, just as there are information processing tasks, such as encrypting information, there are thermodynamic tasks, such as refrigerating. Given that quantum phenomena benefit information processing tasks, can they benefit thermodynamic tasks? How can we extend the Victorian theory of thermodynamics from large classical systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, my field of research. I think that this field shares its aesthetic, its spirit, with steampunk. Hence the name Quantum Steampunk. How and when did quantum thermodynamics develop? The field has roots that stretch back to the 1930s. Right after quantum theory was formulated, people began wondering whether it could explain thermodynamic phenomena. During the 1950s, researchers designed the first quantum engine. It consists of one atom that you can use in a maser. A maser is like a laser, shown here in its all-important function of driving a cat insane. However, whereas a laser emits visible lights, a maser emits microwave radiation. It turns out an engine doesn't need gears and cogs and other moving pieces. It needs only one atom. Over the ensuing decades, quantum thermodynamics had a small following. It wasn't seen as a discipline. Some people even said that quantum thermodynamics is an oxymoron. Thermodynamics was invented to describe big classical systems, such as steam engines. So quantum or thermodynamics couldn't possibly have anything to say about quantum systems. Paul, among others, in his studies of black holes, disagreed. And nowadays, a lot more people agree with the dissenters. Over the past decade, quantum thermodynamics has experienced a boom. Here's a photo from my community's big annual conference in 2018. We form an international community with hotspots across the globe, especially in Europe and Singapore. But I'm delighted to share that now North America has joined the club. As of this month, there is a quantum thermodynamics hub based in Maryland, where we're trying to create a continental community hooked in to the international community. Why has quantum thermodynamics been booming? Quantum information science matured during the early 2000s. It offers a mathematical and conceptual toolkit for understanding quantum systems through how they store and manipulate information. Also, labs achieved exquisite control over tens to hundreds of thousands of atoms and ions. We've been using all of these tools of quantum information science to build and test a theory of quantum thermodynamics. Here's an example. We'll start with a classical story that showcases the interplay between information and energy. Then we'll see what quantum physics adds. We can store a bit of information, not just in a transistor, but also in a gas particle in a box. Suppose that this particle is classical, like a miniature basketball. The particle is a really, really simple gas. We'll say that the gas encodes a 1 if it's on the box's right-hand side, and encodes a 0 if it's on the box's left-hand side. Suppose that we have no idea where in the box the particle is. The position is totally random. Suppose that we want to reset the particle's position to the box's right-hand side, a nice, clean state. This is like taking a messy sheet of scrap paper that's been scribbled on totally randomly and erasing it to a nice, clean state. To erase the bit encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature, through the box's walls. To reset the particle's position, we can slide a partition into the box near the left-hand wall and push the partition to the box's center. The gas ends up trapped in the right-hand side. At what cost? We compress the gas, so we have to exert energy, namely work, the coordinated, useful sort of energy that can be transferred between systems. So resetting the particle's position, erasure, an information processing task, costs work, a thermodynamic resource. When I first learned that in my first quantum computing class, senior spring of college, I was staggered. A priori, information and energy seem like they have nothing to do with each other necessarily, but they turn out to be inextricably bound up. What if we add quantum physics to this mix of information and energy? Well, suppose that we want to erase not a classical bit of information, but a quantum bit, a qubit, a basic unit of quantum information. We can encode a qubit in an electron, such as Audrey's electron from a few minutes ago. Audrey's qubit can be entangled with Baxter's qubits in some fixed temperature environment. Remember, if Audrey's particle is entangled with Baxter's as strongly as possible, and then Audrey measures her qubits, then she has no idea whether she'll obtain a 1 or a 0. The outcome is totally random. So Audrey's qubit resembles the gas particle bit, whose location, left or right, 1 or 0, is totally random. Audrey can erase her qubits while gaining work that she can use to charge a battery or lift a tiny weight. This result should surprise us. We just concluded that we have to spend work in order to erase information. The trick is to sort of burn the correlations between the qubits. Entanglement serves as a kind of thermodynamic fuel when put together with heat. So quantum phenomena can serve as resources in thermodynamics, in gaining work, as well as information processing. Beyond erasing information, we can build quantum thermodynamic engines, refrigerators, ratchets, and batteries. Quantum phenomena can benefit such devices, my community has found. We can use entanglement as a resource in refrigeration. We can charge quantum batteries at a greater power if we entangle them than if we don't. And a quantum engine that, so to speak, burns information can perform more work on average than its classical counterpart can. These results not only help us extend the Victorian theory of thermodynamics into the 21st century, but also help us understand better what distinguishes quantum physics from the everyday world. We gaze into the future of quantum steampunk. What do we see? First, I believe that quantum thermodynamics will spread. Just as quantum information science has transformed other fields, such as thermodynamics, we're using quantum thermodynamics as a toolkit to understand chemistry and materials and more anew. Second, quantum thermodynamics is growing increasingly experimental. Personally, as a theorist, I've collaborated with 4 quantum labs over the past 3 years. One uses photons, one uses ions, and 2 use artificial atoms. We have many options. I expect us to take advantage of them increasingly. Most of the experiments happening now are proof of principle. They show that we can operate quantum engines if we try very hard, but those engines aren't practical. They perform less work, then we have to invest in cooling the engines down and manipulating them. So a third opportunity is to make quantum thermodynamics practical in the spirit of the Industrial Revolution. For instance, I'm working with experimentalists in Sweden on a quantum refrigerator for cooling quantum computers. Quantum thermodynamics is, to me, an incredibly exciting emerging field. It is vibrant and growing. It offers both fundamental insights and technological possibilities. If you'd like to learn more from my book, then you can obtain a discount using this code if you order directly from Johns Hopkins University Press. We can read about steampunk in novels, but this genre of fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. The fantasy of steampunk is becoming a reality. Thank you.
Thank you very much, Nicole, for that crystal clear talk. That was very entertaining and illuminating. I have a lot of questions for you afterwards, but for now, I want to pass it on to our next presenter, who is Paul Davies, and regular attendees of the Ask a Physicist series all know Paul. Professor Davies is Regents Professor at Arizona State University, and he's also the director of the Beyond Center for Fundamental Concepts in Science. He's works in all sorts of areas, from quantum fields and curved space-time to astrobiology and cancer. Well, I'll pass it on to him now.
Thank you, Maulik, and thank you, Nicole, for that wonderful and most entertaining presentation. And I'm clutching a copy of your book, which you very kindly signed for me. It never leaves my side. I really would just like to take up where you left off on a couple of things, because a lot of our listeners, watchers, viewers will be familiar with the fact that quantum physics leads us into a wonderland of possibilities and weird phenomena and processes. And you've told us about some that relate to thermodynamics and information technology. But you've left us with the impression that all of this cutting edge stuff deals really with very tiny effects, with things that you can tease out with individual atoms and so on. And I'd like to ask that if we fast forward, say, 20 years and this technology is developed, will it really be having a practical impact? That is, you were talking about quantum refrigerators, but we're not going to see any effects in our kitchens, are we, on this? So is this just a sort of playground for theoretical physicists, which I love as well as you do, or is it really going to lead to billion-dollar industries?
My answer to that question has multiple sides to it. Until this point, the impact of quantum thermodynamics has been fun theoretical physics, and we've learned more about the nature of reality. Now the community is starting to pivot toward practical applications. I mentioned very briefly this example of quantum refrigerators. I could say a bit more about that and how it could help quantum computers. Quantum computers are a far cry from our kitchens. Personally, I don't expect quantum refrigerators to be in our kitchens in the future. On the other hand, when classical computers were developed, nobody thought that anyone would want a classical or an ordinary computer in their home. People thought that these would be just very specialized devices that very small numbers of people or businesses or governments would want to use. And they were wrong, so I could be wrong. I can give a little bit more detail about this use of a quantum refrigerator in a quantum computer. The idea is that quantum thermodynamic systems do need to be cold in order to exhibit quantum phenomena. So we ordinarily have to invest work in cooling them down. And we also usually have to invest work in controlling and manipulating them. But they're quantum devices, so they put out very small amounts of work, if, for example, they're engines. So we seem to need to invest more than we get out. So I personally have a mission of looking for what I think of as the quantum thermodynamic equivalent of Southern California or Arizona for solar panels. If we put up solar panels in a place like Arizona, then the solar panels are naturally suited to their surroundings. They can basically just sit there, we'll collect power, they'll do their own thing. We don't have to invest much attention in managing them. If, in contrast, we put solar panels up in most other places in the United States, for instance, Buffalo, then we're going to have to spend a lot of time scraping off snow. Sometimes of year we'll get very little power out. So I'm looking for a setting like Arizona for quantum thermodynamic technologies like solar panels, where the technologies can just do their own thing and will benefit. So a certain type of quantum computer is made from superconducting qubits, which are basically artificial atoms made from very tiny circuits. And these types of quantum computers sit inside refrigerators of the sort that I showed that are beautiful and shiny. And those refrigerators consist of many layers, like an onion. The outermost layer is hottest and the innermost layer is coldest. You put your quantum computer in the middle. once the quantum computer has finished a calculation, its qubits are used up. You can think of them as needing to be cooled down even more. We could stick a quantum refrigerator in the center of this classical refrigerator. The center is already cold, so we don't have to spend extra energy to keep our quantum thermodynamic refrigerator cold. We could hook up this quantum refrigerator to also have access to the outside of the classical fridge, the warmest layer. So the quantum refrigerator will be able to see a very, very cold environment and a very, very hot environment. If you have a cold environment and a hot environment, if you have a difference between two temperatures, then you can extract work from it. So this refrigerator can extract its own work from the temperature difference and use that work to cool down this quantum computer after it's just finished a calculation to reset it for the next calculation. That's the first idea that I came up with. People are also applying quantum thermodynamics in creating or proposing quantum thermometers, and I'm looking for more opportunities. So come back to me in 5 years.
The way you describe it makes it sound like magic, and I think our audience, if they know anything at all about thermodynamics, will know about the notorious second law of thermodynamics, which roughly speaking says you can't get something for nothing. It looks like what you're describing are systems that are sort of playing the margins of that. They don't technically violate the second law of thermodynamics, but they don't seem to abide by the spirit of it. And that's just a preamble to asking you, do you think that living systems, which seem to sort of flirt with the second law of thermodynamics down at that molecular level, do you think they're making use of quantum information processing or trickery of the type that you've been talking about?
Living systems are notorious for being high temperatured and full of water and large. In those contexts, it's difficult to maintain controlled quantum information. So personally, I would be surprised if quantum information had a significant impact on living systems, but I try to keep an open mind. And even I have done a little work on exploring a possible model that someone else has proposed.
So let me now ask you another question, and then we probably should bring in the audience, which is really more of a philosophical question. So a concept like information really began in the realm of human discourse. I talk to you and hopefully transfer some information, and vice versa. And yet we've imported that into physics. And it looks like, from the way you've described it, that information has real physical clout. It makes a difference, that it is in some senses like a fuel. Like you can run little engines and things on information. Is this something that troubles you, that we take something, a high level concept from human discourse, and then find has application in the nuts and bolts level of atoms and molecules?
It could feel odd that information is subjective. I gave an example of a particle in a box. If we have information about it, then, well, I didn't quite show this side of the story, but the inverse of the erasure story that I showed indicates that if we know where the particle is initially, then we can trade that information for work. If I know where the particle is, but you don't, then I can extract work, but you cannot. It is a bit strange that information which is subjective can have such a strong impact on the physical world, which we sometimes like to think of as objective. I personally reconcile these two perspectives by labeling information theory and thermodynamics, especially thermodynamics, which involves the physics of information, as operational theories. Thermodynamics is closely tied to agents who want to perform tasks. such as extracting work or charging batteries or powering factories. And these tasks, since they're performed by agents, involve some subjectivity. And so it's the agent who's doing the manipulating and who has a goal in mind that can help us unite the subjectivity of information with the physical impact of it.
Okay, thank you. We've used up, I think, our allocated time, and so Maulik, do we have any questions that you can put to Nicole primarily?
Yes, we do. So I'll just invite people to send in their questions in the chat. So whatever you think of, just type it in. So I think the first couple of questions I want to ask of Nicole are sort of clarification questions. So one of them was, you mentioned, described superconducting qubits as sort of artificial atoms. So Fred Noguer, I hope I'm pronouncing his name correctly, wants to better understand that. So can you elaborate a little bit on in what sense is a superconducting qubit an artificial atom?
An atom has a very important key property, at least from my perspective, and that is that it can have some amount of energy or some other amount of energy or some other amount of energy, but not amounts of energy in between. We say that the possible values of energy that it can have are discrete. They're just specific numbers. And these specific numbers form a certain pattern. We can also, separately from atoms, build, again, very tiny circuits in which that have even cool properties that are rather unrelated to how atoms work. But an important property of these circuits is that we can engineer them to also have just this amount of energy, or this amount of energy, or this amount of energy, but not amounts in between. And we can design this set of possible energies to be similar to the possible energies of an atom. So that's why we could think of these circuits as artificial atoms, because they share this key property with atoms.
Okay, thank you. The next question is from Vishesh Kumar, and he asks, does getting information from quantum entanglement mean that information can travel faster than the speed of light? This is a frequent source of confusion. It troubled Einstein himself because for entangled particles could be very, very far apart, and it sort of looks superficially as if doing measurements in one is transmitting information at faster than the speed of light. So how is that not in conflict with causality? Could you elaborate a bit on that?
Sure. Suppose that I have a particle, you have a particle, these two particles are entangled, and then, as you said, we bring them very, very far apart. And suppose that I measure my particle. Then in a cartoon sense, we might think of your particle as changing instantaneously. And it's at this point then that we say, well, haven't I sent information to you more quickly than light could travel? However, one might say that your particle has changed, but you haven't yet gotten information out of your particle. In order to get information, you need to measure your particle. And in order to measure your particle, you need to know how to measure your particle in order to get out that information. You can measure your particle in any of many different ways. And in order to actually send information to you, I need to tell you how you should measure your particle. I can tell you that only at the speed of light, at the quickest. So in order for you to get the information that I transmitted by measuring my particle, I first need to send you the information of how you should measure your particle.
Great, thank you very much. Well, now we can move on to some more abstract questions. There's a question about about consciousness. We believe that to understand consciousness, as Roger Penrose has proposed sometimes, that we really need to sort of understand quantum computation at some level?
Since living systems are at high temperatures, are very watery, and are large, I expect that we probably don't need to apply our knowledge of quantum effects in order to understand consciousness, because large systems, high temperature systems, and wet systems form environments in which controlled entanglement, quantum phenomena are killed off extremely quickly. So I would be very surprised if entanglement or quantum computation played a role in consciousness, but I don't actually know.
Okay. Well, we also have a question that came in from Barbara Temple, who attends all of her Ask a Physicist webinars. And she asks whether there are any deeper implications of quantum steampunk on the nature of the universe. In particular, could you apply ideas from quantum steampunk to the fabric of space-time itself? And there's actually, in quantum cosmology, there's this idea that we should apply quantum physics not merely to living systems which are complicated enough, but in fact to the entire universe. So is there something we can learn from that approach?
One of my favorite fundamental insights about the nature of the universe from quantum thermodynamics involves what Paul mentioned earlier, the second law of thermodynamics. The second law governs even other theories of physics, such as cosmology and astrophysics and quantum physics and everything in between. What is the second law? One way to think about the second law is that it tells us which transformations can happen spontaneously. Suppose that I have some thermodynamic system. Suppose that I've just taken an apple pie out of the oven. The apple pie is steaming. That steam forms a thermodynamic system. It's initially around the apple pie. Maybe eventually it'll fill up the whole kitchen. We can ask, is the transformation from around the apple pie to filling up the whole kitchen possible spontaneously? We answer this question by basically figuring out what the entropy is of the thermodynamic entropy of the steam when it's in this initial state, and what the entropy of the steam is if the steam is spread out all across the kitchen. We ask, does the entropy increase or remain constant? If the answer is yes, then the transformation can happen spontaneously. In fact, if and only if the answer is yes, the transformation can happen spontaneously. But when we apply the second law of thermodynamics in a situation like this, we actually have in mind some assumptions. For instance, really the second law of thermodynamics applies only to infinitely large systems, although it applies pretty well to systems that are just very large, such as steam in a kitchen. And the initial state and the final state have to be kind of quiescent states that we call equilibrium states. We might want to back away from these assumptions and not have to use them. We might want to be able to ask what processes can happen spontaneously in small systems, in quantum systems, in systems that are far from quiescent states. We can ask what transformations can happen, so to speak, spontaneously for much more general systems. And the second law has been generalized to apply to some of these systems, or to apply to these systems in quantum thermodynamics. The second law has been generalized to a whole family of second laws. Instead of having to check just one quantity, the entropy, and see whether it grows or remains constant during the imagined process, we have to check a whole family of quantities and see whether they grow or remain constant during the process. The idea is we're now able to answer a much more general question, so we have to do more mathematical legwork. I think I see quantum thermodynamics as providing a more detailed view of the second law.
Okay, thank you very much. This next question, I think, is a question that I'll address to both of you, to Paul and to Nicole. And it's a question from Howard Lennis, who asks whether one of the reasons we've not encountered aliens is that they're using advanced technology that we can't detect. So specifically, I'll interpret his question as the following: we have this whole quest to search for extraterrestrial life, to look for to intercept possible signals. But what if the aliens are super advanced and not sending signals using radio waves, but using qubits? If we were to intercept a signal like that, we would probably not be able to make head or tail of it and distinguish it from noise. So, I'll pass that on first, maybe to Paul.
Thank you very much, Modi. Well, the question about are the aliens signaling each other or signaling us often comes up in this connection of entanglement, and does entanglement permit faster than light transfer of information? I think there's this myth that is out there that this provides instantaneous communication across the galaxy, and that somehow if we could tap into this, we would be able to pick up the messages. But I think we've made it very clear that this is simply incorrect. You cannot send information faster than light using quantum entanglement. There's also another issue that I'm sure Nicole could comment on, which is often called quantum cryptography. One of the reasons that we're developing the technology to communicate at the quantum level is it provides absolutely secure transmission of information, because if you try to eavesdrop on the message, you then disrupt it in such a way that it's clear that the message has been compromised. And so actually it's most unlikely that if alien civilization over here and an alien civilization over there were transmitting information using some sort of quantum cryptography, even if we were to interpose ourselves, we would not be able to make head nor tail of the message. So let me see what Nicole has to say about that.
I think that's a good synopsis of quantum cryptography. Since I think less about extraterrestrial beings than Paul does, I'll instead twist this question a little bit to be able to talk a little about information and thermodynamics. The question of why haven't we encountered the aliens? Where are they? If we've been around for so long, surely we should have received their signals by now, was posed by the great 20th century physicist Enrico Fermi. My favorite answer to that question is by Leo Szilard, and it's, the aliens are here. They just call themselves Hungarians. Leo Szilard himself was Hungarian American, and he belonged to a crop of Hungarian or Hungarian American scientists who absolutely transformed physics during the 20th century, especially information theory and thermodynamics. And also, Hungarian, as many people probably know, is a language that is very different from all of the languages spoken around the area where Hungarian is spoken. And so Leo Szilard was basically saying there are these brilliant people who have revolutionized humanity's understanding of science. All of a sudden, they speak this bizarre language that's uncoupled to any other earthly languages. Surely we're aliens. You can even find a Wikipedia page about the aliens, aka the Hungarians. And in fact, if you read my book, then you'll find that Hungarian after Hungarian has made a huge impact on information theory and thermodynamics. And so as we go through the book, we go through a whole lot of these people in Leo Szilard's cohort. And Leo Szilard actually came up with the reverse of the information erasure that we saw at the end of my talk. I mentioned if you have information, you can use it to extract work. And it was Szilard who came up with that idea.
All right. So this next question is from Gerard Milburn from Australia. He asks, does quantum thermodynamics offer any new insights into the origin of irreversibility of the universe? So in other words, into the question of the arrow of time.
I usually think about quantum thermodynamics and its relationship with irreversibility in terms of these new insights about the second law of thermodynamics. Earlier, I mentioned how the second law of thermodynamics, when generalized, for instance, to quantum systems, it splits into a whole family of second laws. Also, if you use a different framework that is arguably within quantum thermodynamics, then you can get even another type of more detailed second law to get different insights about basically the flow of time and how much work we have to spend to get an irreversible process to happen. So I'm less familiar with applications of quantum thermodynamics to cosmology, although I guess I could mention briefly, even I have done something on kind of in the spirit of earlier work of Paul's, putting together quantum thermodynamics with black hole physics. That there is a black holes, if you drop qubits into them, if you drop information into them, scramble up that information extremely quickly with a very chaotic quantum systems. A few years ago, a measure of that amount of chaos or quickness of scrambling was proposed. And it seemed to me that this scrambling up of information, really this dissipation of information across many degrees of freedom, was very reminiscent of the second law of thermodynamics. And one of the incarnations of the second law of thermodynamics, one of these more detailed second laws of thermodynamics within quantum thermodynamics. So I ended up proving an equation that was one of these more detailed, more refined second laws, but for this context of information's getting scrambled up in a system like a black hole.
Okay, we're almost out of time, so I think I'll maybe end with there's a question from Jason Yallen, who asks, a common engineering problem with quantum computers is how noisy the qubits are. So what does quantum thermodynamics say about better controlling the signal to noise ratio? Can we use quantum thermodynamics to improve or to control the noise?
That's a main goal of mine in the experiment that I mentioned recently, building a quantum refrigerator to cool qubits in a superconducting qubits quantum computer. If the more that we cool qubits, the less noisy they become. So the idea is to use a quantum thermodynamic technology to reduce the noise in a quantum computer.
Suddenly you're muted.
Yes, okay, all right.
I think we're out of
Yeah,
time.
well, we're just about out of time. So I want to thank everybody for coming to this Ask a Physicist webinar, and we look forward to seeing you next month. And thank you again to Nicole for speaking here today.
Thanks very much for hosting me.
Bye-bye.
Thank you and goodbye, everyone.